Okay, thank you. So, okay, so yesterday at the end of my talk I was interrupted, so no, I start again with this general type definition, so in order to fix ideas. Okay, so let me say something a little bit more general, okay, for line bundles. So suppose you have a holomorphic line bundle on a compact Kähler manifold or projective manifold, whatever. So you want to define when L is big. So you have several definitions. So yesterday I gave one. So if. So you look at the growth rate of sections of tensor power of L. And you want this sequence of natural number to grow polynomially, like a constant times m to the dimension of x. This is the definition of being big. So this is one definition. Or, so for each m integer such that the linear system is not empty. So this tensor power is effective. Then you can look at the Kobayashi map, which is a map, a holomorphic map to some projective space, and it's defined on X minus the base locus of the line bundle. So this is the locus where all section vanish. And then you go to the projectivized space of H0 X L tensor M, say dual. And you take a point here, and you go to the hyperplane here of sections such that at X they vanishes. This is a hyperplane because we're not in the base locus. Okay, and so you look at this, and you say that L is big if for some m, this map is birational. Okay, that's an equivalent definition. You can prove them to be equivalent. It's not immediate or obvious. Sorry?
Everything should be birational to image.
To its image, exactly. Thank you. And let me give another definition, another characterization, which is so-called Kodairas lemma, which would be useful in what follows. So L is big if and only if for every ample line bundle on X, you have that some power some big power of L tensor with A minus 1 is effective. Okay? So bigness means that even if you subtract a little bit of some positivity, if you take some multiple of L, then at the end you will get some section at some point. Okay? So this definition, this is Kodairas lemma. So this definition is quite useful if you consider this condition of being big from a differential geometric point of view, so in terms of curvature, okay? So it will be useful later, so I continue with this sort of parenthesis here. And so, so the well-known Kodaira theorem tells you that being ample is completely characterized in differential geometric terms and in terms of positivity of curvature, okay? So the theorem is that a line bundle is ample if and only if it is positive. Positive meaning that you can put on it a smooth emission metric whose Chern curvature, which is a 1-1 form, a real 1-1 form, it is positive. Meaning that if you write it locally, the coefficients form an emission matrix, and this matrix should be positive definite, okay? And so this thing here permits you to construct metrics on L which are still positive, but you have to quit the smooth world of smooth emission metrics. So you need to consider more general metrics, which are just maybe L1 log locally. And you take L1 log because to compute the curvature, you have to take derivatives. And L1 log ensures that you can compute derivatives at least in the sense of distribution theory, okay? So I don't want to transform this lecture in a positivity theory, complex vector bundles and so on. So I will be sketchy and brief, but nevertheless, so this means, in particular, that. So what does it mean? So suppose you have something like this. So when you have, in general, when you have an effective line bundle, you can construct a metric on it, singular, as follows. So that's effective. So by definition, you have a section. You take this section, and you declare that this section, point-wise, has norm 1. Okay? And of course, this has to be singular at some point, because at some point this section vanishes, and nevertheless you say that at this point has norm 1. Okay? So there is something going on singular. Okay? But so let's see how to construct a positive, in some sense, metric on L, singular sense, starting out of this. Okay? So that's the plan. You take HA, a metric on A, smooth. So such that, let me call I theta of A HA. So this is the Chern curvature of this metric. So, and this is positive. Okay, this exists by what I've said about Kodaira's theorem. Okay. Okay. Now, on L tensor M tensor A minus 1, you have a singular Hermitian metric, say H, which is the one such that our section, our chosen section, has norm 1. Okay? And now, okay, again, I'm not so precise and I'm a little bit sketchy, but nevertheless, so now you can compute this curvature for this bundle. Okay? This will be not no more a 1-1 form with smooth coefficient, but what is called a 1-1 current, okay? And has a 1-1 current. So 1-1 current is something which is, it's in the dual of form, okay? It's like distribution for function, okay? And has a 1-1 current. This is exactly the current of integration over the zero locus of sigma. So what do I mean by this? So associate to sigma a divisor in X, okay? And this is no more a 1-1 form, but it's something acting of on n-1 form, okay, by duality. And the action is given by you take this n-1 form and you integrate over this divisor, okay? So if your n-1 form is positive in some sense, meaning that the restriction on the divisor gives a positive volume form or something like that, okay, this will be positive, okay? So this is a positively curved singular metric, okay? Okay, but now, out of this data, you can construct something on L. So if you take, so this is positive 1-1 current. Okay, and now you take the metric H, you tensor by the metric HA, okay, and you get a metric on L power M. Okay, this is a metric. Okay, and then you take the mth root. This is a metric on L. Okay, and so now you compute the curvature of this guy here. Yeah.
HA is the current, which is HA.
HA is the smooth metric here.
That one.
Yeah.
Okay, thank you, sorry.
And this gives you, you compute, okay, and this gives you 1 over m, the curvature of L tensor m tensor A minus 1 with respect to H plus 1 over m I times the curvature of A with respect to each HA. Okay, so you have these two terms. This is positive in this weak sense of currents. This is indeed a Kähler form. Okay, this is a positive 1-1 form. Okay, and so all this is greater than or equal to 1 over m I theta A H I. Okay. So, and this inequality is in the sense of currents. This is some positive current. So if you erase it, you get something which is smaller in the sense of currents. Okay. So what all this means is that given a big line bundle, you can give it a singular metric, and whose curvature in the sense of currents is not only greater than or equal to 0. Okay, but it's bounded below by some small multiple of something which is positive in the usual sense, in the smooth sense. Okay, so you are away from 0. Okay, and observe that this metric has a locus where it's not a true metric, as I said, and it coincides exactly with the point lying on this divisor, right? Because you're declaring that this section has norm 1, so where it's singular is exactly where it cannot be cannot have norm 1 because it's 0. Okay, so the singularity of this metric are concentrated on this divisor. Okay, so that's the general slogan that you have to keep in mind. Okay, it will be not fundamental to really to handle of this, but at some point I will use this to prove some vanishing theorem. So you just have to keep in mind that you have positivity of curvature and singularity along the divisor given by the section you have chosen here. Okay? Great. So now with all this, now if you apply one, no matter one, these are all equivalent definitions, and you take for L the canonical bundle, so if X is a smooth, say projective manifold, you take L to be Kx, okay, and X is of general type if Kx is big. Okay? So you see immediately from the definition that if L is ample, then it is of general type. Okay? So if the canonical bundle is ample, then X is of general type. And if X is singular, then it is of general type if some, hence any, resolution of singularity is of general type. Okay, so if X is singular, maybe the canonical bundle is even not defined on X, right? So you just go to some resolution of singularity, and you ask that this resolution of singularity has big canonical bundle. Okay, and this is you can show that that's independent of the resolution of singularity. Okay, so. With this in mind, maybe I can state again the conjecture I was stating yesterday. Okay. Okay, so let me state 3 conjectures. The third one containing the first 2. Okay. So the first conjecture is Kobayashi, 70s. Then if X is hyperbolic, then Kx is ample. Two, Green and Griffiths. This is 79. Even if after several years that I started looking at these things, I realized that in this paper that everybody cites, there is no such conjecture stated, right? But I don't know. Anyway, too late. Okay, so if X is of general type, then there should exist some proper submanifold of X containing all entire curves. Of X. I state the third one that I already stated yesterday, and then I comment on this. So this is long 86. X, say projective. Then X is hyperbolic if and only if X together with all of its subvarieties is of general type. Okay. So they are connected, these conjectures, okay, as you can see. So for instance, you see that if X is hyperbolic, then by this conjecture it should be of general type, which is not very far from being ample, but still, okay. So why it should be ample, Kx? Because if you specialize this direction of this conjecture to just top dimension and dimension 1, you get that X is of general type, and also there are no rational curves in X, okay? And by standard arguments like cone theorem and base point free theorem, all these standard arguments in MMP, you get that the canonical bundle must be ample, okay? So since there are no rational curve, first of all, it must be Neff, big enough, so it's semi-ample, and then you look at the Kodaira map, the Itaka map from the canonical bundle. If it's not an isomorphism, you have in the exceptional locus you would find some rational curve, something like that. Okay. So this implies this one, okay, and you see if X is of general type, okay, then this conjecture tells you that entire curve must sit in some proper algebraic subvariety, okay? But if the proper algebraic subvariety is again of general type, you apply it again, and you shut down the dimension, and at the end of the day, there are no entire curves. And by Brody's theorem, X must be hyperbolic, okay? So this is the interconnection of these conjectures. Okay, so not very much is known about these conjectures, okay? So let me recall you just a couple of results about this. So for 1, this is known in dimension at most 2. So this is basically two things. There is the birational classification of surfaces plus the fact that K3 surfaces are not hyperbolic. Okay? So to prove such a conjecture, you need the classification plus something in Kodaira dimension 0. Okay? And that's why even if we have more or less classification in dimension 3, the conjecture is still open in dimension 3 because you don't have the same thing for Calabi-Yau's. Okay? Calabi-Yau threefolds are not known to be not hyperbolic, even if it's likely, maybe, I don't know. Okay, if I knew. Okay, and so 2, so this is classification plus non-hyperbolicity of K3s. Okay, so then for conjecture 2, yeah.
How do we see that K3 are not hyperbolic?
In several ways. In the projective case, for instance, you know by Bogomolov-Mumford that there are always rational curves in it. And in the general but here it's okay also for compact Kähler case, and that's the fact that Kummer surfaces are dense in the modular space of K3s. They are not hyperbolic because they obtain starting from a torus, right? And the property of being hyperbolic is open in the Euclidean topology. So yeah, so by limit. So there is something about Calabi-Yau's in dimension 3, some partial result, but just for very high Picard number. Okay, so what about 2? So there is this famous theorem by Michael McQuillan, and I am supposed to talk about that in the last lecture, but yeah, we will see. Okay, so McQuillan, So it's okay if dimension of x is equal to 2. All this is trivial in dimension 1, okay? So McQuillan, okay, tells you that it's okay if dimension of x is equal to 2 and C1 square bigger than C2. So these are the Chern number of x, okay? And if you look at the web page of Michael, you will find a FAQ page where he explains that it's also okay for 13C1 square greater than 9C2. Okay? Which is better than the previous one. Okay, so this inequality here are not just magic like this, but they are, I mean, the difference here, C1 square minus C2 or 13C1 square minus 9C2, are the leading term of some Euler characteristic of some bundle, which
the second inequality, I mean, or it's just Michael McQuillan wrote this in some paper, the second inequality, or it's just the same inequality?
It's in the FAQ, yeah.
There is a proof? In the FAQ, there is a sketch of proof, or no?
No, there is a proof. There are several papers.
Yeah, there are several papers. Yeah, it's resolution. It's resolution of singularities for. I mean, you need resolution of singularity for foliation by curves on threefolds, which has been done with Daniel Panazzolo, and I mean, yeah.
Okay, thank you.
I mean, yeah.
It's like 1,000 pages.
Yeah. Yeah. So if you want to read it.
1,000 McQuillan pages.
Yeah. You have to multiply. There's a factor. Yeah. So anyway, so this C1 square minus C2 and 13C1 square minus 9C2 are the leading term of the Euler for the Euler characteristic of some bundle, which provides, and this inequality assures in some sense that this bundle is big, and you have something to start working with. But we will see today which are the bundle in question. Okay. And three. I mean, more or less, it's what is known about three is more or less the sum of these two. Okay. Okay. So for three, you have some particular cases in when you can verify this direction. So you take some particular classes of hyperbolic manifold, and you want to test if it's true, if all subvarieties are of a general type. Okay. And so now there are several cases. So let me say this also. So testing this direction. Okay. So this is okay if. So three remarkable cases are the following. So X covered by a bounded domain. In Cn. So this is what I was saying yesterday, done by Sébastien Buxam and myself. If X has a metric with negative holomorphic sectional curvature, this is Genancia. It's very recent, last summer. And a little bit less recent, it's the case of X being a projective hypersurface general and of high degree. Okay, so the fact that such an X is okay for this direction of the conjecture is very far from being trivial. Okay, so the fact that such an X has all subvarieties of general type It's a theorem which is done by Clemens, Voisin, Pacenza, and others. Okay, and the fact that any such x is hyperbolic, it's a very recent theorem by Damian Brodbeck, and it's hard. Okay, so. But nevertheless, these are examples where this direction of the conjecture can be tested. Yeah. Yeah, also. Yeah. Thank you. Okay. Yeah. Yeah. There is a number if it exists. I don't know. It's a very huge number. I don't know if it exists or not. Yeah. It's explicitly. Yeah. It's n to the 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 n. Yeah. Right. Okay. So now what's going on? Is it okay? Yeah. Okay. Okay, so what's going on? So suppose that x, okay, let's suppose that x is compact, okay? So by Brody's theorem, being hyperbolic is equivalent to not having entire curves, okay? So if x is not hyperbolic, by contradiction, suppose you have some f from C to x, holomorphic and non-constant. Okay? And without loss of generality, we can suppose that f prime of 0 is different from 0. It has to be different from 0 somewhere, right? So why not 0? Okay. Now, what are we going to do? So since f prime of 0 is different from 0, it means that locally around 0, okay, you have an embedding of some neighborhood of 0 in C into your x. So you can look at f of this neighborhood as a submanifold, one-dimensional submanifold of x. Okay? Let me state like this, okay? It's embedded, okay? Okay, so now you pull back your metric, omega. Omega is a 1-1 form on X. Now it's a 1-1 form on C, right? So write it as 2i lambda of t dt wedge dt bar. Okay, observe that this lambda of t is nothing else than the norm with respect to omega, the square norm with respect to omega of f prime. Okay? So these being different from 0 or equal to 0, it's the same thing as different or equal to 0 for f prime. Okay? Okay, but now we look at some disk of radius r inside C, and we restrict everything on this disk. Okay? R can be taken arbitrarily large because you have a map from the whole C defined to your manifold. Okay? Okay, so on this disk, you have the corresponding Poincaré metric. So we saw yesterday for the disk of radius 1, you rescale, okay, and you have the Poincaré metric, which is given by 2i r square r over r square minus modulus of t square square. Okay, and the curvature is still minus 1. Okay? So the general philosophy of this Schwarz type lemma, Schwarz peak, alpha Schwarz, and whatever, is that, of course, a priori, if you have a map from the disk of radius r into a manifold with a metric, you pull back the metric, and there is no reason why this metric should compare in some sense with the starting one, right? You have this guy here on the disk, and you also have this f star of omega restricted to the disk. There are 2, 1, 1, 4. Why should they compare? I mean, but the philosophy is that if the metric on the target has negative curvature, then you are able to compare these two metrics. Okay? And you have something like this. Some inequality here. Okay? And here there is a constant depending on the negativity of this metric. Okay? So say that this is less than minus I, less than 0. Okay? And so you have some 1 over A there. But we are going to see how this works. Okay? We want to compare. Okay, so so if you see this thing at point where f prime is different from 0, it's really an embedding, okay? And so this guy here can be seen as the restriction of omega to the image of C. Okay, just the restriction. So when you compute, so at point where lambda is equal to 0, this is not a true metric, okay? But we are far away from this now. Okay, we are around 0. So at this point, this is a true metric around 0, okay? And if you compute the Gaussian curvature of this guy, okay, it's the same thing as if you compute the holomorphic sectional curvature of f of C inside X, okay? But this, you know that is bounded above by the original sectional curvature of the manifold, okay? So in particular, if compute kappa of t, which is 1 over lambda of t, d square dt dt bar log of lambda of t, this is the Gaussian curvature for this metric, where it is a metric, okay? And this is bounded above by minus A. Okay? Because this is bounded above by the holomorphic sectional curvature of the original metric, okay, in the direction of f prime of t. Is it okay? Yeah? Am I alone or no? Okay, okay, good. Okay, so now on delta r, we consider the following function, lambda of t times ar squared minus, okay? So basically we are considering the ratio of f star of omega and omega delta r, okay? But this is an advantage, this function. So lambda of t is bounded, of course, because it's smooth and we are looking on a compact set, okay? And non-negative. And this is 0 on the boundary, right? So either this function is identically 0, but that's not possible because I'm assuming that lambda of 0 is different from 0, okay? Or you have some absolute maximum for this function, and it will be in the interior, right? Not on the boundary, because it's 0 on the boundary, okay? So you pick some t0, where this function here has a maximum, okay? But then, since log is increasing, okay, also log of the same thing has a maximum at t0, okay? And now we use what is usually called the maximum principle, even if it's just the fact that at a maximum point the Hessian matrix is semi-negative, okay? And in particular, it's trace, okay? So we compute the Laplacian of this guy at that point, and the Laplacian must be at most 0, okay? But the Laplacian is just, I mean, up to a constant 4. It's just this guy here, okay? So we compute this thing for log of that guy here at t equal to t0. And this is less than or equal to 0, okay? And also, of course, lambda of t0, it's different from 0, okay? So we compute this. So logarithm of a product is the sum, right? So we have one term which is d over dt dt bar of lambda of t, and it's up there, okay? So this term is minus lambda times k, okay? So this is minus lambda of t times k of t. And then you have this d over dt dt bar of this guy here. And you make the computation, and you obtain minus r square over r square minus, so sorry, this is t0, okay? Okay, that's a computation. That's the same computation which shows that the metric has constant curvature -1. Okay, and so what you obtain is that k of t0 lambda t0 times r square minus t0 square over r square is greater than or equal to -1. And this implies that lambda t0 r square minus t0 square is less than r square over a. Okay, where we use this fact. Okay, that's a mess because you have all this negative thing, and when you divide, you have to turn the inequality. But I think it's correct. Okay. Okay. But this guy here, it's our function, our starting function at point t0. Okay, but it was a maximum. So in particular, it's bigger than our function computed at 0, right? And at 0 is just lambda 0 times r to the 4th. Yeah. And so you get the lambda 0 is less than or equal to 1 over a times r to the r squared. Good? And now you let R go to infinity. And this goes to 0. And so you obtain that lambda of 0 is 0, which is a contradiction. Okay? So this is the proof of Alford-Schwarz lemma, okay? Hidden in this, okay? But so you see what I was saying about compare. It's here, okay? Because in general, here you have that this is greater. So this is a parenthesis here. Coming back to that compare, this is greater than or equal to lambda of t times r squared minus modulo of t square square. Right? Because that's a maximum. So you can divide by r squared both of them, and you get exactly that. You can compare those two with this constant a. Okay? Because you divide by r squared, so this is gone. You have 1 over a, and you can compare them. Okay, that's the general principle is that you can compare metric on the disk with the Poincare metric, provided this metric is negatively curved. Okay, that's the slogan. Okay, so in the last 5 minutes, I can do the rest, what I was supposed to do in 1 hour. So, okay, so. Okay, so this is very, very important, okay? So this proof you have to try to understand a little bit, because it can be generalized in several other things, in several other ways, sorry. And for instance, it can be done when this lambda can go to minus infinity somewhere, to plus infinity somewhere. You have very much singular versions, but the philosophy behind is always the same. It's that you can compare these two metrics, okay? So maybe before finishing, I can just give you one example of something. So tomorrow we will introduce these jet differentials, okay, which are differential equations which try to govern the geometry of entire curves. So let me give you one motivation for this, okay? So take some holomorphic map from C to Cn. Okay? And then you can take derivatives, and derivatives are still mapped from C to Cn, are vectors, okay? And suppose that you take the first derivative of f, then you wedge it with the second derivative, and you go on till the kth derivative. Okay? And suppose that for some reason, this vector field on Cn, this function to Cn, is identically 0. Okay? That's a differential equation on f, right? Then, the image of C is contained in an affine subspace, affine linear dimension n minus k plus 1. Okay? So you have this holomorphic map to Cn, and you suppose it satisfies some differential equation here, and you deduce an algebraic degeneracy of this map. Okay? The image has to be contained in some linear subspace. So how do you prove it? So without loss of generality, we can suppose that k is greater than 1, right? Otherwise, it's just constant. And that f prime wedge f k minus 1 in 0 is different from 0. Okay? So we are saying that if we go one step behind, then it's not identically 0. That's the first meaningful equation that you have. Okay? And in particular, you require that at 0 it's not 0. Okay? So in particular, f prime of 0 is not 0. So in a neighborhood of 0, in C, there exists lambda j holomorphic function such that so you can write, by definition, in some sense, you can write the kth derivative of f as a linear combination of the other ones, right? So you can write it as sum for j from 1 to k minus 1 of lambda j of t time f j of t, right? And now you take derivatives. And inductively, you see that at 0, all the derivative of f are linear combination of these guys here. Right? And now f is an entire, it's an entire map. So you just take the development at 0, and everything can be written as a linear combination of these guys, the derivatives appearing in development, and so it must be contained in some linear subspace which is spanned by these guys here. Okay? So that's a very easy example, but everything, I mean, jet differential, it's this. Okay, you have a differential equation, and you have and with these differential equations, you want to show in some sense algebraic degeneracy of entire map. So what we're going to see tomorrow is how to construct such things in general on manifolds, and how to use them to deduce property of hyperbolicity. Okay, stop here.